As we learned earlier in this session, feed-forward neural networks are present in many areas of our society. But until recently, the applications of neural networks with backpropagation were still somewhat limited, and researchers followed other avenues to tackle the most complex machine learning problems. Artificial neural networks went out of fashion mostly for two reasons. The first reason was that computers did not have enough power to allow researchers to train big enough networks. The second reason was that there was not enough data available to train deep networks in an interesting way at interesting tasks. It is not that no one tried deep networks. In fact, Ukrainian mathematician Alexei Grigorievich Ivanchenko and colleagues trained an 8-layer deep network successfully in 1965. But since the turn of the millennium, there has been an accumulation of technical developments to scale backpropagation and make recursive network works better. And more importantly, we now have a lot more data and way more computing power. Neural network resurfaced in the form of deep learning around 2007 when Jürgen Schmidhuber and his students broke the world record at speech recognition with their long short-term memory, or LSTM technology. In 2009, they won the cognitive handwriting recognition competition with the same type of network. In 2009, two students of Kenyan researcher Jeffrey Hinton trained another 8-layer network and beat the state-of-the-art on speech recognition. In 2012, it was already being used in the Android and in the cloud Google speech recognition systems. Hinton became Google's chief AI researcher. As of fall 2016, all the speech recognition systems use backpropagation as their core technology. In 2012, a new dataset for object recognition was released that had millions of tagged images instead of the thousands that had been available up until then. This was enough to allow neural networks to quickly beat the state-of-the-art on object recognition. Deep learning is, in a way, just the modern name for artificial neural networks. But it works like never before because of the amount of data and the computing power that is now available. One of the main tricks that makes deep learning computationally tractable is to train one layer at a time, starting with the data. The first layer will learn low-level features and correlations in the data. Then you use this first layer output as input data to train the next layer. And then you proceed training the layers one by one. Because the networks are deeper, they can take lower-level information. So, for example, instead of feeding the network features of the data, as you would usually do in machine learning, you can feed it raw data. And the network's first few layers will compute the relevant features for the task at hand. This is called representational learning, or feature learning, because the system is in fact learning how to best represent the data, provided there is enough data. This is one of the biggest advances that has allowed deep learning to break all those records. Feature design had been the bottleneck of machine learning since its beginning. We can train the network in unsupervised mode with a lot of unlabeled data. This is called pre-learning. Once we are done, we can train the network with gradient descent or with gradient descent through time if it is a recurrent neural network, and with the little bit of labeled data we have. This means that we can set all the weights in the right zone for the type of data we are dealing with and use a little bit of training data to adjust those weights. The small amount of training data we have would have not sufficed to train the network if we started from scratch. The technique is a type of semi-supervised learning, using a lot of unlabeled data and only some labeled data. Eventually, with enough data, pre-learning is not necessary anymore. The idea of training the network with a lot of unlabeled data and then doing supervised learning if necessary with a small set of unsupervised data is really similar to what happens in real life when human learns. You see objects every day by the thousands. When you see a new type of object, you only have to be told one or two times this is a motorbike to be able to recognize all of the other motorbikes. You generalize that knowledge. This strategy is again called semi-supervised learning, and is the best one so far when you have a lot of unlabeled data, which is usually the case, and only a limited amount of labeled data. To put it in images, this simplified diagram shows the approach used for object recognition. To process this input image, the network looks at the pixels in the image. The first few layers will generalize, finding, for example, age detection on the first layer and corners and contours in the second layer. It may identify parts of objects in the third layer, and then eventually we recognize objects at the deeper layer. Like for feed-forward network we learned together, designers have to make choices about the type of neuron and their activation function. Is it a linear unit, a rectified linear unit, a sigmoid unit like the one we studied, or others? Then there are choices about the architecture, how the units are connected. The architecture could be a feed-forward network, it could be a convolutional network, a recurrent network, a Boltzmann machine, a deep encoder, or an adversarial network, etc. There are a variety of architectures and types of networks that have been proposed. Some types of networks that were not so popular became more popular once we started being able to stack them. A good example is the restricted Boltzmann machine. As we record this, it is used by Netflix for their recommendation engine. Fully connected neural networks do not scale very well when the dimension of the input is really large, as with images. If you have a 30 by 32 pixel RGB channel, that is about 3,000 features on the input layer. If you consider a 200 by 200 pixel image, this is 120,000 features on the input layer, which means that each of them will be connected to a lot of nodes. The number of weights to update if you have several layers quickly becomes very big. Working with images requires finding tricks to manage the size of those networks. As of 2016, the biggest neural network we can train is about 1 billion weights. For now, what we can do with this big network is amazing, but still limited. The future is bright. Convolutional neural network is one of the approaches that allowed progress in computer vision by explicitly assuming that the inputs are images, that is, two-dimensional grids of pixels. It makes use of this assumption to gain some computational power. The neurons are arranged in 3 dimensions, width, height, and depth. Convolution is the idea of having a neighborhood of pixels that is projected onto one given pixel. Here, for example, you have a 5 by 5 grid that is projected to a 3 by 3 grid by using 3 by 3 grid masks. Pooling is the idea of downsampling a grid of pixels. In a convolutional neural network, we have an alternative of convolution layers and pooling layers to simplify and abstract the image for the network. Those layers do feature extraction and representation. Both convolution and pooling abstract the data and help building up invariances. The idea that things can be at different scale and with different orientations. Also, the dimension reduction is helpful to avoid overfitting. Eventually, at the end, we can train a classifier with a little bit of training data to get back to human understandable representation. Another big advance is in recurrent neural networks, where the basics of vanilla recurrent neural network is not efficiently trainable. In 1997, Jürgen Schmidt-Huber introduced the long short-term memory, LTSM, which made backpropagation through time technically feasible. There is a lot we can do with recurrent neural networks nowadays, with sequence-to-sequence recurrent neural networks, encoder-decoder LSTM, and bidirectional recurrent neural networks. Recurrent neural networks are the top of the art in many domains too. As of 2016, LSTM, for example, is used by Google Voice Recognition and Translation. As we briefly mentioned in our introduction to machine learning, there are 2 types of machine learning. There is discriminative learning, where we learn to map from the data to the label. Technically, it is about learning the posterior probability of the data. That works well for supervised learning. Then there is generative learning, which is more general. In this style of learning, the goal is to learn enough about the data to be able to generate new data that looks like the training data. The principle behind this type of understanding is what I cannot create, I do not understand, as Richard Feynman famously said. The idea is that those networks are trained to actually hallucinate the types of data they have seen. Here we learn the whole joint distribution of the data, or the distribution of the data and the label, if you wish. From that distribution, you can easily guess the discriminative task back if needed. There is a move toward generative models that are now made possible by the availability of computational power. In conclusion, there is a real renewal of the connectionist approach to artificial intelligence, and the areas of progress are too numerous to be described here. Suffice to say that new connectionist models of human cognition are emerging and the validations are human competitive at tasks as complex as object recognition and language translation. With the rise of neuroscience and deep learning, connectionism is becoming the dominant paradigm in cognitive science and artificial intelligence it once was again.